Work? Yeah. Very good. All right, welcome to this session. So I'm leading the AI and software group at the European Space Agency for the Director of Human Spaceflight and Robotics Exploration.
Yeah, Felix here. I'm CEO and co-founder of PaleBlue, trading simulation company.
Yeah. And actually, what we wanted to present you today is it's a kind of collaborative presentation between ESA and PaleBlue. So we have contracted PaleBlue to develop a specific training system to train astronauts. And I will present a bit what my group is doing, at least from the XR part, because we do many other things first, and then how PaleBlue is actually inserted into this ecosystem of ESA with a contract.
Take this time with a slide.
Oh, yeah. All right. So for those in the room who do not really know ESA pretty well, so we are composed of 22. Of 22 member states. Austria is one of them. And we build rockets. We have space missions at different levels. We build satellites. We train astronauts, and that's the reason why we are here today. We watch over the Earth with Earth Observation Program, also in collaboration with the European Union. We explore space. We landed on Titan, which is the farthest point where a human craft has ever landed. And of course, we are trying to solve the science equation. What we do in our lab is actually many things. We do training, design, research, visuals, and as well as tech development, as you can see. So for instance, in these little pictures, you see some examples of some XR projects we have been conducted. Some of them are XR, some of them are more flat screen, some of them are more 3D. So that's, in a nutshell, the portfolio of what we do. Then if I go to next slide. Our destinations, especially for the Directorate of Human Spaceflight and Explorations, are Earth. So Earth analogs, Earth itself. Low Earth orbit. Low Earth orbit is our jargon to say the ISS, the International Space Station. We go to the lunar orbit, and we go also to the lunar surface as well as Mars. So my lab is supporting all these destinations. And when we talk about training, again, the topic of today, we train not only astronauts, but we train also people on the ground, and there are way more people to be trained on the ground than astronauts.
Thank you. Couple of words about PaleBlue, company based in Norway. We specialize on training various professionals, XR, not XR. We've started 10, 11 years ago with training of commercial divers. And today we train on a wide spectrum of different jobs. We work with ESA, of course. We work with NASA Johnson Space Center. We work with our clients in the energy vertical, and we also tailor to public education and healthcare sides. So over the years, we've developed and shipped many different kinds of training for different kinds of operations. And in this 25-minute slot, we'll talk specifically about the VR and XR training for astronauts. But before that, I want to hand it back to you, Lionel, for the work you do.
Yeah, so we don't only do training for astronauts. As I said in the introduction, we also do classical XR applications. I think I clicked too many times, so it's going to...
Oh, yeah, animations. Yeah, the most...
So one of the things that we do is as we go to destinations where normally we don't go, so we cannot show you very good pictures, very good renderings of destination where we go. We usually, my lab is doing some representations, some visuals of things where we go, or objects or spacecraft we're gonna try to finance via our different ministers. So for instance, if wants to work. Yeah. So you see a couple of examples here where we were trying to put some image on some projects. For instance, the lunar lander in the upper right corner is the main project we're working on to launch on the moon a significant large lander. We are embarked finally on having a kind of cargo capability up and down to low Earth orbit, and later, hopefully, with astronauts. This is this visual. We are creating rovers and some experiments that you can see here on the bottom right corner. But also, we have also some technological developments, and essentially when we go in space, we want to make sure that XR is usable, and it's not only useful. So one of the things we are facing is actually tracking in space, and we will come back to this with Felix. XR tracking in space is it's a bummer. It's a complicated equation, so we are working on that. We are working on assistance for astronauts. As you can see here, it's a full body tracking system that we are developing to assist the astronaut for medical operations, so you don't have always a doc next to you in case something goes wrong. We are co-designing also with industry some haptic elements, as you can see in the small animation. We do parabolic flight, again, to validate some of the technology. And in the upper left corner, you can see that we have worked on displacement of terrain. Whenever you walk on the moon or on Mars, you will then reshape the terrain with your vehicle or with your footsteps. And it's essential for us that the terrain is modified if you need to dig, if you need to drill, if you need to explore. So we do this kind of development as well. Some other research we also do. We work also with some various companies, as you can see here, to explore a bit VR on the water, because to train astronauts underwater, which is similar to the weightlessness conditions, you need a significantly large pool with a lot of safety issues with the depth and everything. So our idea was, what if we try to explore VR on the water? So you will reduce the size of your pool. This is one of them. One of the other also aspect that we explore a bit, as you see in the upper left corner, is exploring the haptics aspect. We took the logbook of Apollo missions, and some of the pitfalls during Apollo missions could have been seen before if we would have had XR simulation and training systems. For instance, here is the deployment of a radioisotopic generator on the moon, and we are trying to see, have we seen that if we would have the XR technology back then. And again, you see here a little lander. We were trying in the early stage to see if we can reproduce correctly the surface of the moon and all the features that you have on the moon. All right. And if we talk about the moon, as you can see here, we have a kind of little videos of something we have done where you see an astronaut approaching the lander, trying to get access to one of the deployed payload on the side of a lander. And for that, we wanted to see if the reach, the ergonomic of the lander we have designed is compatible with the spacesuit. You can see that the field of view is obstructed. And you can also play with the time. So the little other video here with the little wheels, you can change the time of the day, any time, to see that if you conduct this operation today, do I have solar reflection on the solar panels? Do I get blinded by the sun? Do I get long shadow, etc., etc.? And all that, it's a kind of first steps towards a digital twin of the moon, right? And to validate all that, we also have a lunar analog that we just inaugurated in Cologne in Germany, and we even designed this kind of big 700 square meters lunar sand using VR. So it was more an architectural development. Right, and of course on the training side, and then I will hand it over to Felix, you see a couple of images of all the training we do for astronauts, the upper left being PaleBlue. We also do a simultaneous training of 3 astronauts at a time to get familiar with the space station. This is what you see here. They get familiarized with the outside. The inside is done by PaleBlue. We also are running directly on board the space station VR. So where actually we have astronauts wearing the goggles to get trained directly inside the space station, because the retention is much better. The immersive aspect, as you all know, is much better in VR. So we train them just 1 day prior to the operations, much better than a year before. We also train anatomy. We train also on robotics in mixed reality. So we are using different providers so that we can bring a real object into the scene, like control panels, joysticks, and stuff like this. And we export also our software to our NASA colleagues so that the training of the astronauts at NASA and at ESA are more or less the same whenever they fly to the space station.
All right, excellent. So I don't know how many people in the audience have seen this face before. All right. One, thank you. This is Marcus Wandt. This is a Swedish astronaut that recently has been trained on our XR systems. Then he flew up to the ISS on Axiom 3, if I'm not mistaken, came back, and he meant that XR and virtual reality training was instrumental in understanding the layout of such a complex facility as the International Space Station, understanding how to navigate in zero gravity, because we simulate that, and also understanding of the various procedures and emergencies that you could encounter while up there in space. So this is him. This is Marcus under training in Cologne, and you see a bit of a background in with our software. You see the headset for the PC-based VR that we've been using. So just now, we'll cover some aspects of building training for training astronauts. What does that entail? And specifically, when we're building training to simulate the International Space Station zero gravity. One important part, of course, of this is the modeling of the station. And I'll tell you that for the International Space Station, the CAD model, if you get hold of the CAD model, it won't necessarily give you all the details that you want to do. Of course, there's quite an elaborate job to recreate the station from the outside, and even more sometimes from the inside, just because it's really massive. And it has the US operational segment, the Russian operational segment, the Columbus module, the Japanese module. And when we are thinking what a space station looks like, I think we have this image in our minds given to us by a number of science fiction movies, that it's kind of this sterile, well-lit place that is boxy. But the reality is different. The reality is that when we as humans, we populate any room, it tends to be filling up with mess. And that's one of our jobs, really, to add this realism, because that's a part of the experience of being at the International Space Station. So we ended up creating specifically what we call mess modeling tools, so that we can populate like cables and small objects throughout the station. And we are not coming exactly one-to-one with the reality of things up there, but I believe we're getting pretty close. We can also talk about hardware, because for the hardware, for a massive and a very complex model that the International Space Station is, and also for the intricacies of modeling zero gravity in a simulator, we have to have pretty well established and powerful computers. So that's why our main setup for training is a desktop-based VR with Vario, and we'll also compile the same and optimize it to run on standalone setups such as Meta Quest 3. So maybe you, Lionel, could tell us what are the use cases between these two.
Yeah, it's very good. Actually, when we do classical training, when the crew is in our premises or at NASA, they train with the left setup, which is PC-based, pretty beefy, pretty big. But they express the need of having the option of training by themselves when they are in the hotel room, or before when they are in quarantine, just before launch. And therefore, PaleBlue has developed this portable device, Quest-based. So therefore, there are these two devices.
Right, and your left setup is running on 4090 RTX, yeah. Not 9040, as I said earlier. 4090, thank you. And we support a number of input methods. We do support hand tracking, but we also support a wide set of various controllers. Here again, you see Vario setups, the Finnish headset that you'll see a lot through the expo. I think today, which is this high definition, very powerful, very crispy image headset. One thing that we are lacking in when using hand recognition is ability to press a button to invoke some advanced functions of your body, and therefore we are running gesture recognition as well. With this, it's kind of a non-trivial on how would you approach simulating and controlling your body in zero G. So when you're putting on the headset, you're floating around inside the International Space Station. So what's the most natural way and body posture to have when you're going through a simulation and training like that. So this is one of the examples that we did, and we've tried a number of other setups. Let's see if the computer will help. Yes, thank you. So what's the conclusion of the different setups that we use for body posture?
Yeah, the body posture, the high stool is probably the best one, although we thought that lying on a chair, reclining chair is the best, but then you get blocked into your elbows, and then the gym bench was kind of okay-ish, but in the end it was tiring after 5 or 10 minutes of training. So at the end of the day, the high stool is the best and non-rotating, and then Felix can say a few words about that. So it's actually easing the training because we just need a high chair. That's all.
Right. And what you said there with the what's called zero gravity chair or the garden chair, what we found out when you're operating in zero G, especially on the inside the International Space Station, you do work a lot like with your peripheral zone, and therefore you need to push off walls and brush off walls and really navigate to propel yourself forward. And if you have any sort of a chair that obstructs or kind of limits this movement, such as the wider chair, it's not desirable. So therefore we went to this setup, which is a high stool that doesn't really obstruct your movements. But the setup that you've seen here is the swivel chair. We found that is not something we want to have because, end of the day, we want you to be facing one direction when using the simulator. Otherwise, you will have a disconnect between how your virtual body is oriented and how your physical body is oriented. So you want these two to be in alignment because you want your virtual knees and legs to be in a certain position. In addition to body positioning, we've also looked into haptic devices. I don't know if this is losing battery. Oh yes. So haptic devices, we are for getting signals when you're touching something because you have fairly good control. A lot of the challenges connected in navigating in zero gravity is really understanding where your body is, especially where your body is below your waist. Just because you don't have gravity, you don't really walk around and you know perfectly where you are. So the moment you're putting a virtual reality headset, how do you convey that you've touched something with your feet, right? So that there's any contact in the lower body part area. And therefore, ESA has come up with these haptic devices.
Yeah, we created these haptic devices just to give you some impulse on any part of your body which is touching any structure. And as Felix said, this is pretty important for us, especially for the design review. So when we do design review of new space modules that we put around the moon, we want to know that, do you have a certain reach? So can I reach that from where I am? But if I start to be halfway inside the table, I need to feel it. Because in VR, you could be, and then you have a false impression that you can reach your object. And you will validate your requirements like, oh yeah, I can reach it. But actually, you have a massive collision. And there are very little devices on the market to tell you, hey, you have collision. So therefore, we developed that. PaleBlue also developed a kind of visual system, like a kind of radar telling you...
Damaged radar, yeah, damaged radar.
Yeah, so that's an alternative. So we are evaluating both.
Right. Okay, so hardware side, if we look more into the system and its functioning. So we've built a number of iterations of character designs. We've started with rather simplistic characters. We added more details lately. We've added hair systems. We've added movable jaws because what you'll see, the training is multi-user, multiplayer. So you want to see other people talking, you want to talk to them. So you really want to have visual feedback on when someone is looking in a certain direction so that we can have integrate gaze direction on your model and also jaws movement. And we're coming to locomotion, which is one of the most foundational and important elements. How do you actually move around in zero G? So this is why we had to create an extended physical engine that really allows you to propel yourself by pushing off surfaces, by grabbing handles, as you would be doing in actual zero gravity. So a lot of computational complexity, of course, comes into this physics modeling. And of course, you're not just simulating the astronauts, you're simulating the boxes, the CDBs, you're simulating others. It's a complex modeling task. So with that, there's a number of interactions that otherwise should be possible, from grabbing objects, tools, doing complex interactions and such. So this is just showing examples of propelling yourself and navigating throughout. So we do integrate a number of scenarios, emergency scenarios, donning and doffing of various spacesuits. So anything from like docking with the SpaceX Dragon to the station, doffing the suits, exiting the Dragon, and also getting the cargo boxes into the station, and emergencies as well. So the design you see on the left is when you put on a gas mask. And yeah, if we're talking here maybe specifically about the origin of this training, why do we need to train in VR?
Yeah, so one of the original idea of that is normally we train all 7 crews or 6 to 7 crews simultaneously. They have to be gathered and assembled in Houston to be trained at the same time in a mock-up. And one idea is like if we can co-locate this training using smart systems like what you see here, then people will be able just to train from a distance, remotely join a session, either fully virtual or kind of hybrid. And this was essential, so it means like people here can train with people in Norway, can train with people in the US, and at the same time, emergency scenarios, as you can see, floating object, the behavior of the smoke, the behavior of fire, you cannot simulate that on the ground because of gravity, and VR gives you this option. So that's pretty good. And also in the fact that you wear emergency equipment on your face will change your voice, will change how far people will hear you, and that's all simulated here.
Right, so what we are seeing in here, of course, is various emergencies, trainings with smokes and fires and multi-users. So you have several people working simultaneously to address fire. And the same goes to how various physical structures behave in zero gravity, like hatches and such, because you will see a big difference in like your everyday training on Earth and how would they behave in zero G. We've been expanding the simulation to include various lighting modes. Not many people know that there's day and night at the International Space Station when you switch off the lighting. And even then, if you have some issues, you put on the headlamp and you're able to go around and specifically address what needs to be done. And also, so we kind of address this by pre-baking a couple of different lighting modes throughout International Space Station, but adding dynamic lights on top of that, so that, you see that there's some accent lights from your LEDs, from your communication devices, but also your headlamps or your flashlights that you'd be using for the actual operation. In addition to training and equipment testing in, close quarters facilities, ESA have been doing a number of parabolic flights, and we as PaleBlue, we've joined on some flights to test equipment and also do motion capture. So maybe you could say something about testing the equipment for zero G.
So zero G, as I said in introduction, is pretty difficult to enable a good tracking in space. So this parabolic flight, and we have done several of that, was to test several solutions to get rid of the IMUs you can have in any headsets and try to have either optical-based tracking or tracker-based. And we find out a solution. So that was one of the main objectives. The second objective of this parabolic flight was to capture the proper zero-G motion so that the zero-G motion could be then reproduced in the VR systems, because an essential thing in training is whenever we bring new technology like this one, people will always argue that, hey, what does it bring to me? And aren't we entering the territory of negative training? And we have to prove them, like, look here, the zero-G moves, as Felix said, and you can see in the video, were captured properly in the zero-G flight, in parabolic flight, to make sure that the moves you do in VR are the one that you are supposed to be doing on board the space station. And several crew tested the system as well to make sure that, if I rotate my wrist, I push myself away, it's correct.
Right. Okay, so we are soon out of time. Just to add another use case to the parabolic flight, of course, one thing is the equipment testing, another thing is the motion capture, but it's also foreseeable with hybrid astronaut training when we are training this in the parabolic planes, but at the same time we're having a VR image of a different space station. So with the last animated sequence to show in here, I will ask Lionel, what is the future for this technology in human spaceflight. What's next?
Yeah, so the what's next was we first of all started to train some of our astronauts, especially Axiom 3. Axiom 4 is currently training with this system to get used to the space station and the zero-G moves. But the next big step will be to use that system to validate many aspects of the new space station we are building in collaboration with NASA and also with the United Emirates to put around the moon, a moon base around the moon. And to do that, we will validate many of the requirements in the design using this zero-G engine and also many of the technologies which were tested here, like lighting conditions, shadowing effect, how to open and close hatches, moving boxes, and all that. And that would be essential for us. And then once we have passed the design phase with our colleagues from NASA, then we will go to the next step, we will be training whoever is flying there and whoever is on the ground. And as you can see, most of the features you have seen here are immediately transposable to moon exploration. And then when we will go to the surface, we're already working on that, we will have similar simulators for the surface itself in habitats, landers, and rovers.
All right, and that concludes our presentation. I hope we have a couple of minutes for questions.
Unfortunately, we ran out of time, but you will be around the session later. So if anybody has any questions, then feel free to reach out to them. We will take a really short break, a couple of minutes, and then we will back with the next talk. Thank you so much. That was super unique insights. Super happy to have you.
Thank you.